Hello, my name is Andrea Wingenroth, and today I'm going to be performing a process capability analysis. And this is my submission for MSE 425 Exam 3/Final. So let's start with the problem. We are given a table 6.3 in the textbook, with the inside diameter measurements of forged car engine piston rings, and we are given 25 different samples with 5 different observations for each of these subgroups. We're also given the upper and lower specification limits for production for the customer, and our objective is to use process capability analysis to quantify process variability relative to product specification. The question we will be answering is the process capable of producing parts within specifications? More specifically, is the production process capable of producing piston rings that are within the given tolerances? All right, so let's have a look at the table first. This is the table we are given, and we can see that there are in fact 25 samples with 5 observations of inner diameter each. These inner diameters are measured in millimeters. To answer our objective question, we need to talk about process capability. Process capability refers to the measure of uniformity of the process. In this case, we are looking at instantaneous variability. This is the variability in a critical to quality characteristic at a specified time. We're going to be performing a process capability analysis, which is a formal study to estimate process capability. This estimate is usually in the form of a probability distribution. Oftentimes, specifications or tolerances are taken into account. However, these are not always necessary for process capability analysis. In our case, we will be using specifications. So the assumption, we are given the assumption for the upper and lower specification limits as 74 plus or minus 0.035 millimeters. We will utilize this given assumption in Minitab. So anything above or below these limits is considered defective or non-conforming. So a piston ring size above 74.035 millimeters or below 73.965 millimeters is non-conforming. So there are a few basics to understand about process capability analysis. A process capability study measures parameters or characteristics about the product in question, not the actual process itself. We can say a process is capable when these parameters are consistently within specification. We can analyze data using control charts. Problems arise in process capability studies when standard deviation is too large or the mean is not centered between the two limits. Here we can see a basic example to show how process capability is measured using a 6 sigma spread of the product quality characteristic. In this picture, we can see that the quality characteristic in this specific process has a normal distribution, and we can see that the mean is centered. We can also see that there are 3 standard deviations to the right and left of the mean. This is where our upper natural tolerance limit and our lower natural tolerance limit are located. For a normal distribution, we can see that 99.73% of parts or measurements are within tolerance for this process. This means that only 0.27% of the process falls outside of the natural tolerance limits. We can see that to the right of this and to the left over here. Although 0.27% sounds small, this means that 2,700 parts per million are non-conforming. The less defective parts we can achieve, the more capable the process is. This also means that for a more capable process, a company is producing far less waste. So the ultimate goal is to see quality improvement in any process. The main results we can see from process capability analysis is that we can 1, predict how well a process will hold the tolerances, and most notably, number 7, reduce the variability in a process. These are important for producing parts for customers that are within the given specifications, and again, reducing waste. Histograms, probability plots, control charts, and designed experiments are all used in process capability analysis. Now, let's head over to Minitab and actually run outputs for the table we are given. All right, so now we are in Minitab. I went ahead and put all the data from table 6.3 in the textbook into Minitab. Here we can see that we have the 25 samples, which each are a subgroup, and then we have the 5 observations for each sample. So we're going to go to Stat, and we're going to go to Quality Tools, and then we're going to run, we have 2 options. I'm going to go ahead and choose Capability 6-pack and choose Normal Distribution because that is what we're assuming the distribution is. And we'll see if this is true later on. So like I said earlier, we have subgroups across rows of these 5 columns, and we have 25 subgroups. So I went ahead and chose the observation columns, and then I inserted the upper and lower spec limits. And remember, this is 74 plus or minus 0.035 millimeters. Then I'm gonna hit OK. And this is the output we get. You can see we get 6 different things, and we will analyze this back in the PowerPoint. But I wanted to go ahead and show you another thing. If we go back to Stat, and we go to Quality Tools, and Capability Analysis, Normal. We're going to do the same thing. We insert the subgroups and the upper and lower specification limits. Just going to double check settings. I went ahead and included the confidence intervals so we can see what it comes up with. Other than that, everything looks okay. So we're gonna see what Minitab outputs. So we are given an entire report. We have lots of statistical outputs, and we can analyze this back in PowerPoint. All right, so let's analyze the results we got from Minitab. So we're given several control charts, and the first one is being this X-bar chart. We can see that the points vary randomly about the center line here. The center line is the average of all subgroup averages. The random orientation about this center line means that the process is stable enough to perform capability analysis. So this is a good thing. Next is the R chart. This chart plots subgroup ranges. You can see that the points are randomly distributed and lie within the control limits. This is the lower control limit, and this is the upper control limit. And we can see that none of these points lie outside these limits. There appears to be no trends or patterns between the data points, so process capability analysis may continue. If you see in the bottom left, we have the last 25 subgroups plot. The points appear to be randomly and symmetrically distributed around the process mean, which is a good thing. You can see that there are some areas of variation. We have some sort of outliers, if you want to call it that. But overall, this plot looks pretty good. Then if we go ahead and look at the capability histogram, the process data appears to be fairly centered, only shifted slightly toward the upper specification limit. We can see that the center between these two, the upper and lower spec limit, is 74, which would be right here. And we see that the mean is at 74.0012 millimeters. So the mean is shifted about 0.0012 millimeters to the right. The process spread is just within spec limits, which suggests good capability. We don't have any points lying to the left or the right for this particular set of data. And then if we actually look at the curve, the normal curve they give us here, we are seeing that the red line and the dashed black line are basically the same. So we can say that the variation in the process overall and the variation of the process for each subgroup are basically the same. There is not much of a difference in their spreads. So in terms of the upper and lower specification limits, and there's not much of a difference between their standard deviations. We have a similar, one's not steeper or smaller in the middle than the other. They're basically the same. You can see they lie pretty much on top of one another. So then we look at our normal probability plot, and we see that we have a p-value of 0.892, which is greater than the alpha risk of 0.05. And this shows that we can evaluate the capability of the process using a normal distribution. All right, so here are some important terms we need to understand in order to analyze a process's capability. CP is the process capability ratio and comprises of the specification limits and the standard deviation. The greater the process capability ratio, the greater the amount of conforming parts produced by a given process. And we can see that the upper and lower specification limits are defined by the customer, and the standard deviation is defined by the process. In practical applications, the standard deviation is estimated using the sample standard deviation. This is denoted by the symbol above the C and sigma, but they are basically the same, just a difference in population size. And P is the percentage of specification band used up by the process, and of course the confidence interval can be calculated as well. All of these equations are used by Minitab to compute the outcomes we see. All right, so we were able to achieve a process capability report in Minitab, and here we can see that the process capability ratio is 1.16. And if process centering is taken into place, the ratio is 1.12. The further away the process mean is from the center, the smaller the CPK value will be. And we can recall from a previous slide that our normal curve was shifted slightly towards the upper specification limit. So this makes sense. If we look down here, we can see that 650.64 parts per million are expected to be defective overall. This relatively low value of non-conforming piston rings shows that the process is capable. Then if we go ahead and look at table 8.2, we can see that our findings of capability for the process of producing piston rings match. We are assuming that the process mean is centered, thus we're looking at CPK, which is this value of 1.12. So if we look in here between 1.1 and 1.2, we see that we should have a number of defects between 318 and 967 parts per million, and that does line up with our 650.64 that we got. This further proves that we have normally distributed data, and the process is in statistical control. And the confidence intervals, which we can see here, shows that this specific process could have quite a bit more or less conforming piston rings, but this doesn't really disprove that the process is capable or not, since capability is relative. All right, so now we have made it to the conclusion, and I will be able to give some recommendations to improve the process. So overall, the current process for producing the forged piston rings is capable. Some samples were close to the spec limits. However, all samples in the study were within specification limits. So although this process may not necessarily need it, we are always looking for ways to improve a certain process. Some ways we could improve the process would be to increase the specification limit range and decrease the standard deviation. This would increase the process capability ratio, meaning that these changes would produce more conforming parts and increase capability of the process overall. So this concludes our findings for the process capability analysis of Table 6.3. I hope you enjoyed it and have a great day. Thank you for watching.